Hello, 3C students. Let me get you started with this spreadsheet in which you will calculate the propagated uncertainty in the frequencies of the normal modes. That's your experimental frequencies and your theoretical frequencies. You already collected some data here. Some of these rows with asterisks are for data input and others are for formula input. So you hopefully measured the mass of that sample string at the front of the classroom, that's lowercase m. Some of you actually just took your own string up to the front before you tied a loop in it and measured its mass and its length. So for those of you who actually weighed your own full string, the same one that you used to do the lab, your L prime would be the same as your L down here and also here. But most of you, I believe, went up to the front of the classroom and there was a sample piece of string. The mass of that string is little m. The length of that string is L prime. And you would use those two numbers to calculate the mass density. Now you'll notice I used non-SI units here, grams and centimeters. So you'll want to do the conversion within this formula here. I think that's the best way to do it. Instead of just taking little m and dividing by m equals, click the cell for mass divided by, and then I click on the cell for length of the string. You would also need to insert some conversion factors in there, right? Because there's 1,000 grams in a kilogram and 100 centimeters in a meter. Okay, you get what's up with that. Here is where you would enter just the vibrating portion of the string. Maybe the string that you had at your setup was 2 meters long, but only 90 centimeters of that was actually vibrating. That's the distance from the stem of the oscillator to, what would that be, to the top of the pulley. Down here, it's up to you to estimate your uncertainties. Since you used the, what was it, the digital scale? I think we had a digital scale up front for estimating, or excuse me, for measuring the mass of the sample string. That's a very precise measurement. So the absolute uncertainty should be small. And I don't remember what the precision was, but if the scale gave you the mass to the nearest, let's say 100th of a gram, then your uncertainty could be 100th of a gram. I believe it gave you the mass even more precisely, maybe 1,000th of a gram. So it's up to you to pick a number that's reasonable. Same thing for the hanging weights. Maybe you took the mass values that were printed on the weights themselves and you took those at face value, like if it said 50 grams, you just went ahead and plopped 50 grams into the column over here. Hopefully you checked those by putting at least one of them on the digital scale to see how accurate that value is that's printed on the mass. So if your mass said 50 grams, but then you put it on the scale and it was actually 50.02, well, then I guess your uncertainty is something like 0.02 grams. So there's no one right answer here, but there is such a thing as an unreasonable answer. So if you've got numbers here that don't make any sense, I suppose you might lose a point or two. This one, you can make a, excuse me, you should be entering your numbers in this column, not this column. It's a little easier to come up with a value for the uncertainty in the vibrating string length because remember, one end of the string is wrapped around the pulley. So it's not totally clear where that node is. Is it at the center of the pulley wheel or slightly off to the side? And then when you look at the other node at the stem of the oscillator, that node may not actually be at the stem. It could be displaced by a half a centimeter or so from the stem itself. And by stem, I mean the little part that poked up from the oscillator that you attached the string to. So pick a reasonable number for that uncertainty. Obviously 5 centimeters is too much, right? You should have been able to judge that length to within an amount less than 1 centimeter. Okay, similar considerations for the sample string length. You had to stretch it out and measure it with the meter stick. You know, if the ends of the string are frayed and maybe you actually stretched the length a bit by pulling it taut, then there's some uncertainty there as well. Pick a number that makes sense. I think 1 centimeter might be a little too much, but that would be a reasonable answer. Now for the uncertainty in your experimental frequencies, some of you used the old-fashioned function generators, where you could only enter frequencies to the nearest integer, like 56 hertz or 57, nothing in between. So it's pretty clear that in that case, you only know what the standing wave frequency is to within the nearest 1 hertz. You were looking for the frequency that produced a standing wave with the largest amplitude. For those of you who used the Pasco equipment, where you could actually output a frequency to the nearest 10th or 100th, something like that, honestly, because I haven't used that particular interface very much, I can't give you a good answer. Oh, got a leaf blower in the background. I'm not too familiar with what the actual precision of that Pasco machine is, so you're welcome to just go with 1 hertz also. I'm not sure whether the frequency that actually comes out of that interface really is what it said on the computer screen. So go ahead and go with 1 hertz for that as well, if you'd like. Now, this next part is really easy. Over here, you just have to convert your absolute uncertainties, which have units, into your relative uncertainties, which are ratios. So for the relative uncertainty in the mass of the sample string, you would say equals, take that mass, divide it by, take the uncertainty in the mass, that's this number, and divide it by the mass itself, and you'll get a ratio there. Now, depending on what those numbers are, you might get a decimal here with like 7 digits. Let's strive for clarity in the spreadsheet. We don't care about all those extra digits, so make adjustments here in the number of digits that are actually displayed. 2 digits ought to be fine. This one requires the use of that formula for propagated uncertainty that I talked about briefly in class, and it's also in the other video that's linked here in assignments. So because the mass of the sample string and the length of the sample string are both uncertain, those uncertainties propagate and cause an uncertainty in the mass density. That's important because we use the mass density over here to calculate the theoretical standing wave frequencies. And since we can't be totally sure of what the mass density is, we can't be totally sure of what the standing wave frequencies ought to be. So we would like to know just how uncertain is the mass density. Do we know its value to the nearest 1% or to the nearest 10%? Because if we only know the mass density of the string to the nearest 10%, that's going to cause quite a bit of uncertainty in our calculated frequencies. So I guess I'll just give this one away here. That's going to be equal to the square root. So I'm adding in quadrature, I'm adding the relative uncertainties of the 2 quantities that go into mass density. When you look at the formula for mass density, it's little m over L prime. And since that's just a quotient, we can use this rule where all you do is add the 2 relative uncertainties in quadrature. So I'll click on the relative uncertainty in the string mass, and I square that, and I add to that the relative uncertainty in the sample string's length squared. Oops, and I take the square root of that whole thing. Okay, that's what we call adding in quadrature. And that's also going to come out as some ratio. Just keep a couple digits of that. For instance, if this ratio came out to 0.02, that would indicate that there's a 2% uncertainty in the linear mass density of the string. This is why it was important to measure the mass of that string with the digital scale. There's a lot of precision there. We want to reduce the uncertainty in the mass density as much as possible. Okay, so now that presumably you've got all this data, you took this in class, including this column. So here's where you would have hung 100 grams from the string and then 200 grams. It doesn't have to be exactly 100 gram intervals. Some of you had to stop after that because we discovered that if you hang more than 300 grams from the pulley, the stem of the oscillator actually starts to bend a little bit and it no longer vibrates the string with any significant amplitude. Now this part's easy, right, to convert into tension. And here's where, for the first time, let's use one of the capabilities of Excel, which is to kind of, Excel knows that very often we would like to repeat a calculation all the way down a column. So I'm going to say the tension on the string here is equal to the mass in kilograms. So first I have to divide by 1,000, and then I would multiply by the 9.8. So now I have tension in SI units. And if you hover over the lower right corner here and double click, Excel is smart. The spreadsheet application knows that what you'd like to do is repeat that calculation all the way down. And of course, because I didn't enter numbers here, I don't get anything that makes sense over here. But Excel has automatically converted those masses into tensions. Even if this column was, 1,000 rows long, Excel would still very quickly make all those calculations for you. Okay, what about, is this a typo here? No, I'm sorry, it's not a typo. I do have two separate columns, one for the theoretical frequency and then for the absolute uncertainty in the frequency. So there's going to be quite a bit of junk to enter all at once using the formulas. And I'm just realizing I don't want to give away all of this. You're supposed to figure out some of this yourself. Why did I call it F3? Because we stuck with the third mode, the one with 3 anti-nodes. That's why I'm calling it F3. If we had just done the fundamental mode, I would have called this F1. Okay, so here's where you would enter equals. From memory here, isn't it 3 times the fundamental frequency, which is 3 times 1 over 2L. I could do it like this. 3 divided by 2 divided by L. Okay, here's an important point, and I don't mind telling you this because we didn't go over it in class. For each of the subsequent rows, I want to refer to this specific cell when I'm calling the length of the string. So I need to hit F4 on my keyboard. I'll show you one more time. Right after you click on the cell in question, here's the cell for the length. I hit F4, and that converts the cell reference into an absolute cell reference. And if I hadn't done that, then when I double click in the lower right corner here, and it tries to complete the calculation for the subsequent rows, what it would do for the next row is look for a cell here below the cell in which I have the length, but there's nothing there. So Excel would be confused. So if you don't want to do that thing where you automatically advance to the next row in your cell references, you have to do the absolute cell reference using F4, or you could just type those $ directly. That works too. So what I've entered is 3 times 1 over 2L. I'm just using properties of, order of operations there to enter the syntax differently. And once again, I did that because I don't like all these parentheses. I could have done this divided by the quantity 2 times L, but that introduces a set of parentheses that could be cluttered later, depending on how many other parentheses we have to enter. So I just go with 3 divided by 2 divided by absolute cell reference. I know I'm going really slow here for some of you, but better that than too quickly. And then isn't it square root of tension over mu? What we really would have to do now is multiply by the speed, but we know that the speed is the square root. So asterisk for multiplication, the square root of the tension. So I click on that cell divided by, I don't know what I said a moment ago, but I meant to say tension divided by the mass density. So I would click over here, hopefully recognizing that this is another instance where I need an absolute cell reference. So I hit F4 again, close the parentheses. So let's check. I've made 3 cell references here. 2 out of the 3 are absolute cell references because we always have the same mass density. It's the same string for each trial. And we always have the same vibrating string length because hopefully you didn't scoot your oscillator to a different position on the table between each trial. For each different hanging weight, you should have had that distance the same. Otherwise, that complicates things here. So for H7, that was the tension. Because that's not an absolute cell reference, then as we go down and compute each row, Excel is smart. It will know to use the tension in the corresponding row. So I hit enter. Of course, we don't get anything meaningful because I don't have actual values. Let me just make something up here. How about 90 centimeters? And maybe you're realizing, let me just throw some numbers in here. This is just BS, right? I'm just making up numbers. How about a mass of 2 grams for a length of 102 centimeters? And these numbers still are not reasonable because you'll notice that just now I failed to account for the fact that this length here is not in SI units. This length is in centimeters. You'll have to include the appropriate conversion factor in your formula. Maybe you're wondering, well, then what's the point of even putting the length here in centimeters? It would have been better to put the length here in meters, do the conversion before you actually enter the number into the spreadsheet. This is a matter of taste, I suppose, but I personally prefer to have convenient units used when you present the data. It's just easier to think in terms of centimeters for the kind of distances that we're talking about with the length of the string. Okay, so you double click here, and Excel will compute all of the theoretical frequencies given the input data. Now, the experimental frequencies, that's easy. That was also just data. That's where you fiddled around with the function generator or the Pasco interface to get the frequency that actually made the standing wave with largest amplitude, because that's the whole point of the lab, right? We want to see if all the theory that led us to these values actually agrees with experiment. Does the calculated frequency, F3 theoretical, actually match the frequency which does produce oscillations of largest amplitude? And really try to appreciate, when you see how well these numbers agree, appreciate all the theory that's being validated, because there's quite a bit that went into arriving at that formula, the formula 1/2L square root of tension over mass density. We had to use Newton's second law applied to a little tiny piece of string that led us to the wave equation. So we had to use some calculus to get the speed out of the wave equation. What else? The theory of standing waves, where you've got 2 waves passing through each other, and the boundary condition of having a node at either end means that the length of the string has to be an integer multiple of half wavelength. There's a lot of stuff that went into that formula, so it's really gratifying to keep all that in mind and see how well it works. Okay, so consider these values your best estimates of the theoretical frequencies, and these are the actual frequencies. And it's pretty telling just to compare these 2 columns visually. When you're all done, you'll see that the numbers, if you did things right, you'll see that the numbers match up really well. But it's nice to go one extra step and see not just what the best estimates are, but what's the range of probable values for the theoretical frequency. So again, I'm just going to pick an easy number here. Maybe this first frequency you calculated to be 56 hertz. You think that's the frequency at which you'll get a standing wave with 100 grams hanging from the string. Well, you're not sure it's going to be exactly 56 hertz because the numbers that went into calculating that are uncertain. We don't really know the mass density precisely, super precisely, and we don't know the, actually that's the main thing, isn't it? The other thing we're not sure about is these masses, but these are pretty good. I think this is the number with the most uncertainty. So we would like to figure out how this uncertainty propagates to an absolute uncertainty in your theoretical frequency. So note here, this is not delta F over F, which would be relative frequency. This is the absolute uncertainty in hertz. So we're going to do everything all at once. Equals the square root of, and once again, you will add in quadrature the relative uncertainties from your various measurements. But you've got multiple measurements that go into this. I'm trying to remember 3 of them, right? So you have to account for the relative uncertainty in the string length, the relative uncertainty in the tension, and the relative uncertainty in the mass density. Now, I already went over this in class, so I won't belabor the point, but remember, since the formula includes the square root of tension over mass density, then you must have a factor of 1/2 in front of those uncertainties, the 1/2 being the power to which the tension and mass density are raised. So I won't type out the whole thing, but I'll do one right now. So 1/2 times the relative uncertainty in the mass density. And again, I've got to hit F4 to do an absolute cell reference. Then I close the parentheses and then I square it. This is a common mistake. People have to put the power outside the parentheses. You need it inside the parentheses. I would do something similar with the uncertainty and the tension. Remember in class, I explained why the relative uncertainty in the tension is actually the same as the relative uncertainty in the hanging mass, capital N, because that factor of G just cancels out. So you'll have to account for that. You'll have 3 terms overall in here. I'll just put ... Then you would hit enter and just double click to repeat that calculation all the way down. Oops, that's wrong. I left something very important out. Hey, what's this? Oops, I typed this formula in the wrong place. I meant to put it in this first row here. So let me cut that. Yeah, this first row is, or the top of the column is for the label. My bad. Oh, now I have to find this pesky Greek symbol here. Insert symbol. Oh, where's the delta? Okay. Uncertainty in F3. Theoretical. That will be in hertz. So I just showed you how to find the relative uncertainty. But to convert that back into an absolute uncertainty, of course, we would have to multiply that by the actual frequency. So I would click on the cell containing the frequency for that mass and multiply them together. See what I'm doing here? Again, it's like when you go to, if you're shopping for clothing and something is 5% off, let's say it's $100 coat that you'd like to buy and it's 5% off, you multiply 5% of that $100 to get $5. That's the amount that you would, that's discounted. So you have to take your relative uncertainty, which is a ratio, and multiply that by the actual frequency to see the amount by which it is uncertain. So this should be something small, right? Like just 1 or 2 hertz in that neighborhood. And the idea is each of these frequencies will have its own absolute uncertainty. All of these numbers are going to be similar, but you may find that some are a little bit bigger than the others. We might as well just do the calculation individually for each. Okay, we're almost done here. So the last thing would be take that information and make it, present it in the easiest possible way to interpret. So all you would do is just copy paste these masses down here. I just put them again in the spreadsheet so you can easily interpret the final results. Okay, what is the minimum probable value of your calculated frequency for 100 grams? When you put 100 grams from your pulley, what's the minimum likely frequency that will produce the standing wave for the third, or I should say that will produce the third fundamental, not fundamental mode, I'm sorry, normal mode. If I said third fundamental mode earlier in this video, that's incorrect. But we used the word fundamental for the first frequency. I'm talking about the third normal mode. These are all called normal modes. The first one's called the fundamental. Okay, well, the minimum one would be equal to my best estimate subtracted, and then subtract the uncertainty. So easy numbers, forget what's actually typed here. What if this came out to be 57, but my uncertainty was 2? 57 minus 2 means 55 would be the lowest likely. That's the whole idea here is we're not just suggesting a single value for the theoretical frequency, we're suggesting a range of values, which is given by the best estimate. That's what comes out of the formula, but also the absolute uncertainty. So you had to do this propagated uncertainty to get the, excuse me, you had to use this formula for propagated error to get the relative uncertainty in the theoretical frequency. And then you turn that into an absolute uncertainty, and then you just add or subtract that from your best estimate here to get the minimum and maximum ranges. So here I would do, this is equal to F3 theoretical plus the absolute uncertainty in that particular frequency. Hit enter, and I don't think you're going to have to mess with any absolute cell references here. Lower right, you get that little black cross, double click, and it will repeat that all the way down. So it's very easy to interpret. Anybody looking at the spreadsheet can look at this row and see what's the, hopefully, a rather narrow range of values for the theoretical frequency. And then down here, all you do is, well, the minimum experimental frequency, if you used the function generator and it said 56 hertz when you got the amplitude as large as possible, then the minimum value would be that frequency minus the absolute uncertainty, which is over here. In this instance, you would need to use F4 because we're always going to refer to this absolute uncertainty. The idea is each of your experimental frequencies would have the same absolute uncertainty. Over here, you would add, again, the function generator might have said 56 hertz, but the best frequency could have been 57 because you discovered that as you went back and forth between 56 and 57, it was tough to tell which one really gave a higher amplitude of oscillation. So the one you wrote down plus the absolute uncertainty, absolute cell reference, hit F4, and then finish. Okay, and I'm not even asking for a whole lot of concluding remarks here. Just give me a couple sentences about how well this range, for instance, matches up with this range. And the ideal outcome would be that this range is, number one, narrower than this range, and number two, that it would lie completely within this range. If that's what happens, then you should feel really good about the legitimacy of the theory that we're using here. And the other way around wouldn't be so good if the experimental range was inside the probable range. I guess both of those would count as agreement, but let's think about this for a second. The first outcome I described was, it's like saying this, okay, as far as we can tell from the function generator, the actual frequency that produced the third mode was between 56 and 58. Could have been 56, could have been 58, probably closer to 57. And then the theory tells us that it should be somewhere between like 56 and a half and 57 and a half. That really is the best possible outcome, because then it's like nothing about our experimental results contradicts what we were expecting. Like the outcome is exactly what we expected if the theoretical range lies entirely within the experimental range. Okay, so this was a little long-winded and tedious. I won't be this tedious every time, but some of you have had no prior exposure to this error analysis stuff. I used to not do any of this as a student or a teacher, and even though it's a little tedious, if you get what's going on here, you can see it really makes the lab experience more meaningful in terms of recognizing whether experiment matches theory. Okay, and now you're also realizing there's no guesswork here. I just showed you how to do everything. Don't forget about those absolute cell references. Don't forget about making adjustments here in the number of significant digits shown. If you do some division in your spreadsheet and show me like 15 digits in your number, that's just annoying to look at. You might lose a point. Make it easy to look at. Cheers.